I was so I decided to talk about this work, this recent work about the separation logic for negative dependence. Is a recent work that we started with few people at Cornell, Joe Tassarotti at Boston College, and me. I will base my talk mostly on the slide that Jeremy has prepared, so I know the slides, I review the slides, I'm ready on them, but I may have some little problem here and there, so be patient. Okay, so mainly this work is about a concept that can come up quite often when you look at some specific probabilistic reasoning. In particular, one example, which is this notion of negative dependence. One example is the situation where we have some bean and we have some ball, and we throw bean into balls, and we have a phenomenon here that emerged, that is the fact that there is some correlation between which bean is full, and there are some questions on which bean maybe can overflow, and we can think about this through this concept of negative dependence. Particularly, we can think about collision, we can think about overflow, and so on. Now, the more computer science application that we should think about are data structures. In particular, hashing data structure, different kind of randomized hashing. And we can, one classical example are Bloom filters, and we can think about them from the perspective of asking ourselves how they do in terms of collision. So here there is a very simple example that I will use through my talk. It's a very simple example of a tiny data structure. Is just an array, 3 elements, and we have some task, and we want to fill, mainly is the representation of the balls into bean. Example, we have a 3 bean, we have some balls that we can throw in, and what we do is we do some uniform sample on 0, 1, and 2, and we add this to our array. And we just check at some point if we have an overflow. Okay, so if one of the load, so if one of the indices in the load is too big, we have an overflow. Okay. And what we are interested in general is like, what is the probability of having an overflow? So it's a randomized data structure, so we don't want to reason just in a deterministic way. We know that, for instance, if we take a very large number of tasks, for sure we will have an overflow. But what we are interested in is more a probabilistic reasoning, because we have this sample step where we sample from the uniform distribution that level out a bit the things, and so we can have a better bound on the probability of overflow than if we just consider deterministic reasoning. Now, I don't know how many of you have been looking at reasoning using probabilistic computation. I know that often is something that scares away a bit programming language people, and but then there are non-smart people like me that can do it. So everybody can do it. It's something that people are looking more and more to, of course, probabilistic computation. And what is interesting is that we can try to preserve a bit the kind of symbolic reasoning we are all used too, also in this setting, if we find the right abstraction to think about them. And this is a bit the goal of this talk, telling you how we can reason symbolically about this kind of example I show you here, through some tool that we already know, in particular separation logic. Now, the reasoning that one usually do use some other tool which is widespread in analysis of randomized data structure, which are concentration bound. These concentration bound are just a way to give a good bound on the probability of something happening in a more concise way than a straightforward reasoning. But to do this, usually we need to have independence of a random variable. So for instance, if we look at here, there is an example. If we look at the sum of n random variable, then we know that we, let's think about a random variable that maybe are symmetric around 0, and we look at the sum, we know that the sum will be more concentrated than just taking error on each one of them and sum up the error. And so these kind of tools are very useful to give a precise bound, for example, on the probability of overflow. Now, you can think about this as a black box that people use just as a lemma. We have a independent variable, let's apply this lemma, which gives us a function that bounds the probability. So,
sorry,
yeah.
just maybe I missed it, but like the precise f and n and m are going to be determined by the structure of the random variables y?
So they are determined by so yes, in particular, I think yes. So they are determined by the fact that we are doing the sum. That's our operation. So the y, not by the, is determined by the single yi and by the fact that we are doing the sum.
Right,
yes.
And that'll determine for you some particular f.
Exactly.
And some particular m.
Yeah, exactly. Is a sum, mainly they exponentially decrease, like
sure,
with the number of variables.
The sum should be normal, so then
exactly.
Are all your yi sampled from the same distribution?
Yeah, we can think about that, yes. Now, this is used, this tool of concentration bound are used really everywhere, but the on my side. But there is an assumption usually, and is that the variable need to be independent. And actually, this is not the case, for instance, in this example, because the loads of the bin are not independent. But in fact, people have looked into this. So the tool I show you on the left is really used in every area of randomized algorithm. The problem is that usually we assume independence, but in this situation they cannot be directly applied because we don't have independence. But people realize that actually we can still apply them if we study a notion which is called the negative dependence. And namely this tool, the concentration bound, can still be used. What is the idea of negative dependence? Intuitively, it's very simple. Imagine about throwing a ball into bin. The fact that one bin gets filled make another bin less likely to be filled. Right? There is this association, which is like the more bin I have in one, the less bin I will have in another. But, sorry, the more ball I have in one bin, the less ball I will have in another. And this is a form of negative association, and this is what we capture here to prove, then use this black box concentration bound and get a good bound on the probability of overflow. So mainly my talk is about how to prove this negative dependence relation, this intuitive notion that if we have more ball in one bin, we have less in the other, formally. Okay.
Can I ask one more?
Yeah, sure.
This
As
may be a
many questions as you want.
This may be a higher level, like not worthwhile question, but so is this negative dependence, does it have to be about causality, or could it simply be anti-correlation? Or am I thinking the wrong way about this? And I should stop thinking about
No, I think anti-correlation is a good way of thinking about it. It's a generalization, for example, of a negative covariance of the variables.
So you're going to find structural, which means that in some level causal proofs of this anti-correlation.
Yes.
Okay.
We think so. Mainly because we want to reason formally, we will find a way to show that there is this anti-correlation.
Okay, and you're going to do that using formal causal.
Yeah,
okay, makes sense. Thank you.
We don't do formal causal reasoning.
We
do separation logic, so more like standard logical reasoning. We will see.
Over lunch, we'll talk about whether or not that's causal.
Okay, yeah. Yeah, it depends on what do you mean exactly, yes. Yeah, and please ask as many questions as you want. I'm more than happy to discuss, and I don't need to go to the end of my talk, although I will probably do because I don't have that many slides. I will do it anyway. Right, so what is the plan is, so we will I will show a program logic for proving negative dependence, and I will explain it first. This is an extension of a probabilistic view of separation logic that was already in the literature, but where separation logic allowed to reason about independence. Here we mainly show that we can use it to reason about negative dependence. And there are many different kind of data structure that we can analyze. We analyze some in our paper. I will not discuss them here, but I want to stress that we were looking for a tool, for a way of reasoning that is really the way people think about this when they design their hashing data structure. So there is several hashing scheme that can be reasoned about using this tool. But I will just use the simple example I showed you before in the rest of my talk. So let me start with the negative dependence. So in fact, while independence is quite easy to define, and people agree on what is the right definition of independence, negative dependence is much more complex, and actually they appear several different variations of this concept have appeared in the literature for reasoning about randomized algorithm. We will focus on a notion that is called the negative association, which seems quite principle and quite well used. There are more advanced approaches that we are not yet able to understand well how to formally reason about. For example, one notion that seems very popular is strongly Rayleigh function, strongly Rayleigh random variable and processes, but we are not able to reason about those. So let me start with the intuition of negative association. As I was saying before, it's a kind of negative covariance. What is a negative covariance? Suppose that we have n random variable, then we say that they have a negative covariance if when we take the expectation of their product, this is smaller than the product of the expectation. Let me take a simple example. Here we look at two coins, coin 1 and coin 2. Each one of them is a fair coin, but they are flipped in the sense that coin 1 give Oh, no, sorry, I got confused. Here is one of the confusion. They are not flipped. They are the same coin. But when we look at the joint distribution, we have a negative covariance because maybe we get one with the probability. Little confused about what I was saying. Yes, they are fair coins. 0.5 probability of returning 0, 0.5 probability of returning 1, but we can put them together in a way that there is a negative covariance, in the sense that we can build a joint distribution like the one we have here, when the probability of having both 0 or both 1 is 0, and we will have 0.5 probability of having 1 0 and the other 1, and 0.5 to have 1 1 and the other 0. And in this case, we can check, and we have that we have this notion of negative covariance.
Sorry, I didn't fully follow. Why is the for coin 1 being 0 and coin 2 being 0, why is it 0?
Because we pick the joint distribution here, and we can pick a joint distribution where this.
Coin 2 is the backside of coin 1.
Yeah,
So-
you can think about that in
Okay.
this way.
Yeah.
So coin 1 is heads, and then coin 2 is tails. That's row 1.
Yeah.
And then coin
Right.
2 is heads. That is the reverse is heads. And then
Exactly.
Coin 1 is
That's
tails.
exactly what we are.
And it
trying
also
to
has the
express.
funny property that no matter which one you look at, it is a fair coin on its own.
That's right.
Exactly.
That's right.
Yeah.
But
On their own, they are fair coin, but when we look at them, they have the property that Michael described. Yeah. Now, negative association generalize this idea. Mainly, we don't have to really understand all the details, but it generalizes this idea not only to look at the value of the random variable, but also to look at how they behave under some transformation. In particular, we take two transformations, or better, we take families of transformation F and G that are both decreasing or increasing, and we require a property similar to the one we were asking before. Okay, so it's a kind of closure property under functions that are decreasing or increasing. Mainly, no matter how we process the random variable with this function, we still have that the expectation of the product is less or equal than the product of the expectation. Now, as I said, we don't need to understand this definition in too many details, but I can give you some examples. Deterministic variable have this property. This is a trivial example where we don't have randomization, and we can show that mainly both of these sides are 1. Okay? Independent random variable have this property because, in particular, we can think about this as one direction of independence. So for independence, we need equality. Here we have an inequality. This is a way to think about it. The Bernoulli random variable that sum to 1 is an example. And we will think about these actually during my talk. So one-hot vector have this property. In particular, we can think about one-hot vector, again, like the bean, the balls into bean before, like we select one bean at the time, and if we sum up them, we see that maybe we have this correlation. Uniformly random permutation also have this property. So things like shuffling card and so on have this property. Okay? So it's a quite widespread concept that we have for some basic building block that we may want to use. Now, they also have some nice properties. For example, we have some closure property. So some set of negative associated variables are negative associated. So in our example before, we had the one-off vector, we take a subset of them, and we still have this negative association. The union of independent NA is also NA. So, for instance, if we were to take this joint union of these two things, we have negative NA. Another property that is important is that monotonically increasing map preserve NA, and this is where these functions mainly become important. So why this property is important is because if we have a data structure that already has this property of NA, and we apply a function, that is what we do all the time in our program, we know that it preserves the property if the function is monotone. Okay? So, for example, we could do the sum or the product of some of these random variables, and this still satisfies negative association. Okay. So now let's go back to this example. How we want to intuitively reason about the negative association of this example. So intuitively, mainly we have a sampling instruction here, then we do some operation, and this is all we do, right? That's all. That's what we do at each round, and that's it. The operation is a kind of addition. We can show that it is monotonic. We can show that the uniform distribution is NA, I mean multiple variables sampled from the uniform distribution are NA, and we are done. Now, to do this formally is a bit more involved, so let me transform first our program. Let's use this one-off vector that I mentioned before. These are just vector of zeros with 1, 1 in one position, and then we sum up directly this vector. And this show a bit more the monotonicity of the sum and a bit more the NA property, because we already said that these one-off vector have NA property. Okay, so I will replace this. Now, let's note first that we started with the load of 0, and I said that deterministic variables are NA. So we have that this vector of load is the variable in this load are negative associated by deterministic NA. Then we need to reason about the loop, and we do reasoning in the loop like we usually do. So we want to show that mainly it preserves our invariant of having a negative association. And to do this, we see that we do a one-hot sampling. So again, we have this by one. We know that one-hot vector are NA, and then mainly we need to reason about the union of these. The fact that we start with deterministic and we have another negative association, we need to reason about this union, but we will do this in an invariant way because we are in the loop. And then we need to reason about the monotonicity of the map of the addition, and we are done, because now we have proved negative association of all our program. And then we can check this predicate, and we can think about this also as a monotone map. So we can prove that the entries are in overflow are NA, and then we apply our Chernoff bound as a black box, our concentration bound as a black box. Okay. this is the idea. This is how we want to use our contribution. Now, let's see how we can transform this into really a formal reasoning. So this is what we will do, but we want a rule to do this. And to do this, we will use probabilistic. I will start with probabilistic separation logic, which, as I said before, is a logic that people have a look at for reasoning about independence. And then from there, we move to our logic for negative association.
Can I ask you
Yeah.
a question? Back on the previous slide.
Yeah.
So you conclude the NA status of these different sets of variables.
Yeah.
So ultimately, you're trying to show that the final overflow is NA.
Yeah.
So do you have to do this for all sets of variables, or just enough so that what's ultimately assigned to overflow is something that data flowed into it?
I mean, for this simple example, all the variables that we are using flow into the overflow, right?
Right.
Because we don't have any other random variable. But in general, no. You can do reasoning about a subset of the variables.
Okay.
Yeah. If you don't have any data flow going into them.
Okay. And so union and map are the way of propagating NA across the transition relation?
Yes. Yeah. Any other questions? All right. So I think most of you are familiar with separation logic, so I will not say too much. It's a logic that people have used to reason as an assertion language for program logic, for reasoning about programs, where we are interested also in some kind of resource. And the main difference from this to, let's say, our logic is that in our assertion logic, we also have this symbol here, which are star, and the magic wand, which are separating conjunction and separating implication. Now, the intuition about separation logic was, I think, it came up and was motivated clearly by reasoning about state, about imperative program with imperative update of state, in particular for heaps, and the idea of separating conjunction is mainly that we have a situation where we can split the reasoning about pointer. Even if the pointers are correlated, we can still split the reasoning into two different reasoning, and then we can go into them independently. This cannot always be done, but if we can do that, then we can simplify our reasoning about each part of the memory independently. So to give a bit of semantics foundation to separation logic, people have looked at some semantic structure, in particular the classical tool to reason about, to give semantics to separation logic are resource monoid. Resource monoid are just a set embedded with some partial operation, that is the monoid operation. It has a classical property of monoid, is associative, is a commutative monoid, it has an identity, and is also a preorder monoid. Now, the classical example of resource monoid is the one I showed you before. So we can think about the heap model as this kind of a resource monoid. We have pointers, and we can reason about them to resource monoid. Now, what Gilles Bart and Justin Schuh, Kevin Bauer have noted is that we can also think about, and I think this was also not before, but they try to make this emerge more clearly, is that we also have a distribution model which fit this notion of resource model. What is the distribution model? Really, it's a model where we think about probability distribution over memories. And we can think about two probability distribution as described by their map to each element, the probability mass function if they are discrete. And we can think about the operation between them, the monoid operation, as the independent product of the two variables if the two domains are disjoint, and then we can have it undefined otherwise. And we also need an identity element, which can be the deterministic distribution of empty memory. Now, mainly what we think about when we think about this model is really that we are thinking about the joint distribution between F and J. So it's very close to what we already discussed before. We need to take different variables and think about their joint distribution. Now, the key point is that in this distribution model that they look at, independence is the key idea. And indeed, they came up with this logic for reason about independence. So when we have our resource monoid, then we can define our notion of satisfaction. And in particular, in their logic, what they have is that we can have a star product, like in separation logic product. And this will tell us that the variable x and y are independent in the model. Okay? So it's a slightly different interpretation of separation logic. But the kind of rule that we get are very similar to the rule we get for separation logic. We have commutativity, associativity. Here is just some classical example to say that it doesn't change much the way we manipulate these assertions. What changes the meaning of the assertions. Now, the other thing that changed is that we have the same assertion logic as separation logic, but we will have maybe different atomic proposition. So that what need to be sound with respect to the model. So if we take a model where we have a probability distribution, then we can take some atomic proposition that talk about probability distribution. Okay. For example, we can take some atomic proposition that say something about the uniform distribution. For the rest, the logic is very similar to separation logic. What they have is that program are just inv program plus uniform distribution, and they have an atomic proposition for this construction, for the uniform distribution, and few other atomic propositions that are specific to the distribution model. So this will not be interesting for the memory model, for the heap model. Okay? And these are used in the rules, for instance, for sampling. When we sample, we can say that this new variable that we are sampling is uniform, and is also independent from what we sampled before. This is what the rule R sample tells us. And we can also have other rule of separation logic. An example I brought here because it's one of the fundamental ideas of separation logic. They have also a frame rule where they can split the reasoning in the usual way of frame. Now, they have a bunch of side conditions that need to be satisfied, but they can still do reasoning in a framed way. Okay? So this was a quick summary of this work about interpreting separation logic for reasoning about independence.
Can I just confirm my understanding of that? Okay, so this, the first rule, this is a uniform sampling assignment kind of statement.
Yeah, it says
And it says
sample from the uniform distribution and lead it to the variable
and
xr.
then afterwards you have a probabilistically independent uniform sampling of XR from whatever the frame is.
Exactly. So suppose that in phi you have already other variable that maybe you sampled before. Now you have the new variable that you have sampled is independent from the other one. One key point is that here is really the uniform distribution. It doesn't have parameter, because if you have the parameter, then this parameter may be influenced by another probability distribution. For example, if we think about a Gaussian, if I take a sample from a Gaussian and then I use this as the mean of another Gaussian, then I don't have independence.
And in their probabilistic diffusion logic, do they have support for those kinds of things?
No. Okay, any other question? All right, then let me move into our contribution, which is a similar separation logic. Actually is an extension of their separation logic, but where we have a notion of negative dependence. Okay? So in their logic, they have something like this, and if we have the star of a bunch of variables, then we know that these assert that the variables are independent in the distribution model. Now, what we look at is, can we add another conjunction that state that the variable are negative association? Okay. Now, you may say, okay, why do you want another conjunction? First, because sometimes you want to reason about independence and sometimes about negative association. So you need to think about negative association maybe as something that in some situation is easier to prove, but you're still interested maybe to combine it with some other independence assumption. So
I'm sorry, I'm confused on the framing. I thought we said earlier that things that are independent are negatively associated, right? Is there a subsumption relationship here or no?
Yes.
And so independent implies NA.
Yes.
But there might be some theorem you need where you need independence.
Mm-hmm.
So you track this finer property?
Yes.
Okay.
Yes. But there are also, so the situation is a bit trickier because there are situations where it's enough to have NA, because maybe you don't need the independence. But there are also situations where if you have NA and some other property, then you have independence.
I see.
So it is a bit of an intricate relationship.
So you'll get better proofs than the plain independence logic would get, because you have more structure to track what's happening.
Exactly.
I see.
That's the idea. I don't have an example here.
Okay.
But that's the idea. The example I will do is still the one we saw before, where we use only negative association. Now, why we cannot just say, oh, let's redo exactly what they did for independence? We can think about the distribution model and just internalize something like that. This is what we try to do. The problem is that there are several challenges when you try to do this. And so one of the challenges is how to build joint distribution that satisfy the formula that we wanted. So maybe we would like to have some operation plus that put together probability distribution. This is a kind of joint distribution operator, which is satisfying the formula only when the two components satisfy the independent. Now, if we try to do this directly, we run into some issue. For example, one issue is that if we try to some of the issues. So when we try to identify this plus operation, we have that in fact we don't have only one joint distribution that satisfies this. So in some sense, independence has a more canonical witness, because mainly you can just take to the product distribution. While here we have several distributions that may satisfy the same negative association. So it's in some sense bringing some non-determinism. Then when we try to even address this, and we will see that there is a natural way to address this, there is other challenge that come from the rule of associativity and unit that we were not able to solve in a straightforward way, in a natural way. And so we had to come up with something a bit new. Let me start from the first. So the first, as I said, is the situation where we want something like this. We want this product that assert NA in the distribution model, which means in particular that when we have this formula, mainly we want to say that the two variables are negative association with respect to the joint distribution. The problem, as I said before, is that we may have situation where the joint distribution may look something like this, but other where the joint distribution may look as something like this. Okay, so which one do we need to choose? Now, the problem is that the model, the monoid model, doesn't allow us to have this non-determinism. So to solve this, in fact, we need to generalize the resource monoid semantics. And luckily, somebody did it before us, Simon Doherty at UCL. I wasn't sure if he was at UCL or some other London university. But mainly we need to generalize this not to be a resource monoid anymore, but to be something where the operation gives us a set of potential distributions. So we need something more complicated. This is a BI framework. BI is the logic of bunch and implication, which is the logic that is behind the idea of separation logic. And then we need to generalize also the identity element to be a set and so on. Okay? So this is one of the first challenges. Now, the second challenge is, as I said, that negative association, when you try to manipulate it with this BI frame, it doesn't satisfy directly associativity and unit. It doesn't have a good unit. And so to address this, what we did actually was to generalize, or better, to generalize the idea of negative association as I described you before. So we don't, in our logic, we don't reason about negative association, but we reason about something that we call partition negative association, which means that for every possible partition of the variable, we want a negative association. So we ask something weaker, that the negative association is not preserved only by the all set of variables, but even by any, mainly partition of the set of variables. Okay? Now, this is a weaker notion, a weaker requirement, but interestingly, it still has some good properties. And what we show is that mainly, so it has some good properties that are similar to the one we want from a negative association. For instance, the partition of independent random variable R, PNA, union of independent PNA partition is also PNA, monotonically integrated map preserve this property, and so on. And now we can build the logic over it, because we have our BI frame, we have this notion that play well with the BI frame, and then we can do the logic. Now, the logic is very much similar to the one we had before, so I will skip most of the work, but let me stress a few points. First, we have axiom, and I don't have them on the slide, but we have axiom about, for instance, uniform sampling, or better, one-hot sampling. So the sampling of a vector in this space, which then we will use in our example. And then we still have a frame rule. Now the frame rule is a little more tricky, because we need to check some monotonicity condition behind checking some of the other properties, but we can prove a frame rule which allow us to reason again about our negative association in a way that is more local than in the global setting. Okay. Now, in the remaining of my time, I want to go through an example and through the example again and conclude. So let's see now how we prove this example we saw before. I will do again some program transformation just to make it easier for our language. So instead of a for task, we can take just a while. I'm sure you are all okay with this. So what do we want to show? So mainly we remember what we said before. We started from the loads are negative associated because they are deterministic. Then we go into the while, and we think about the invariant, and then we think about the monotonicity property of the addition, about the negative association property of the sampling, and about the reunion. These are the three steps we need to think about. Okay? So, because of the deterministic property, we can already assume that we have the negative association before the while. And what we want is, of course, to prove this invariant, that this is present. Okay? We can do this with a relatively standard while rule. In particular, here is one of the things that I want to mention. We are not, our logic is limited in some sense. In particular, we cannot reason about probabilistic loops. We think we reason about deterministic loops. So in particular, this while rule require determinism of the test. Okay, so it's a deterministic test. Of course, we could try to generalize, but for the people that have looked into this, you know that as soon as you have a probabilistic test, then termination becomes a much wilder question than the deterministic case, because you start to have almost sure termination, and different other notions that people have looked at. One could look into it, we didn't do for this work.
But your logic's partial correctness anyway?
Our logic is partial correctness anyway, yes.
So you can't, even if you had a probabilistic loop guard, why would termination matter?
Is the probability of termination that matter. Is not.
But right, but if it's a partial frankness, then you just case plan on whether or not it terminates. It's not your problem.
Yeah, but you start to have loops that terminate with probability less than 1.
Yeah, but how does it affect?
It affects in the sense that when you want to use like the property to show, for instance, the probability of overflow to be something. Now, if your loop may not terminate, maybe that probability is different. So you need to track the probability maybe across almost sure terminating loop. So almost sure terminating loop are the one that terminate with probability 1.
Right, but so in your logic, you will somehow use the number of loop iterations.
So imagine you had a random task that showed up every time, and then that got into the loads. If the loop didn't terminate, then you'd have more overflows, but you would also never get to the loads.
Exactly.
Or you wouldn't get to the overflow check, rather.
Yeah, to the overflow check. Yeah.
So if the distribution you care about in the end is in any way influenced by the thing that you're doing in a non-deterministic way, then the fact that you got there affects, like you have to know the number of iterations, which means you know.
Yeah, let's say that the probability of overflow in this example is like, it depends on the precise parameter, but let's choose parameter that give us two-thirds, just to take an example. With two-thirds probability, you will overflow, okay? Now, if you start to have a loop that may depend on may terminate with less probability, let's say it terminates with probability 0.5, that would affect also our two-thirds, because it would be 0.5 times two-thirds, the probability now of overflowing. So it affects the final probability.
Yeah, so your final probability will depend on the number of loop iterations.
Yes.
Which in this case is that. But maybe we can talk about it at lunch, because you could still have it depend on that information, but not necessarily have that hold.
Okay, yeah, let's talk maybe at lunch about this. So for let's assume that this is deterministic. Okay. Now we can add some other information to our assertion, so that we indeed guarantee that we are deterministic. For instance, we can say that I is deterministic and task is deterministic, and so we can do this deterministic check. So the logic allows you to reason about determinism versus non-determinism. And you can apply a rule like this only when you have this check. Okay? So we need to reason about this loop. So let's focus in a bit in it. And let's start to reason about it. So maybe we want to show that we have our invariant. And as I said before, we go through one instruction at a time. So for I, we just don't do anything special. We just do the classical or logic reasoning, and we propagate the property. Now, where things become more interesting, so this is the deterministic assignment, where things become more interesting is when we have this sampling. And here we have a rule, actually, okay. We have a rule similar to the one we had before for independence. So here we are stating independence. And mainly we can actually use the fact that independence implies negative association. And so maybe from this, we deduce that not only we have independence, but we also have a negative association. Okay. And so we can do a consequence rule to have our new assertion. We can play a bit with the associativity and so on. And then we can do our updates, which we know is a monotonic map. We need to show that it is a monotonic map, so we have some operation for that. And then we can show that since it is a monotonic map, then we can preserve the negative association. We can propagate from load to updates. Okay, and then we can just conclude our post condition. Okay. So then we do the last step to show that also the overflow are monotonic. So you see the high-level reasoning we did before now has been made formal by this logic, and we have everything to express negative association. We have the different operation that preserve it. In our paper, we presented this at top of this year. We had the meta theory of this logic developed in more details on the rules and the examples. And with this, I want just to sum up. So I showed you today like a logic to reason about negative dependence. In particular, we had to define a new definition of negative association, which is a closure somehow of the definition that was in the literature. We had to prove this notion to play well with respect to the I-frame, and this is what gave us a new separation logic for reasoning about negative association. Now, where we are going from this is that the negative association is used a lot also. Here we look at the example of hash function, but another very popular application of negative association are sampling scheme. In particular, when we have sampling scheme, we want to show that we cover somehow the space well. And so we want to prove property like negative association, which give us a property about the covariance and so on. And this is what we are looking at right now, how to generalize this logic for reasoning also about that. Why is not so trivial? Because when you do sampling, you also have a property of, you need some form of conditional distribution and conditional variable. And those, as Michael know well, are tricky to reason about. And with this, okay?
Any questions?
I have a couple of, whoop.
So Robin or Dave?
Yeah.
Dave go first.
Yeah, so thank you, Marco, very interesting. You mentioned, so it's a weakening of the separating conjunction in this setting. You use that property, but are there any surprising algebraic properties that come up for this thing?
So one is not too surprised. I'm not sure it's a surprise property, and is not very algebraic. But for mainly define our when we define our model, mainly we have that we need somehow, or we use somehow a family of these stars. So this star is not just one, but is a family of star indexed, you can think a countable family, which has some nice properties. So it's a family of product. And actually, mainly is a kind of new way of thinking to like families of separating conjunctions, which actually we happen to use also in another work, which is completely independent from this, on reasoning about metric spaces. So it's not really an algebraic property in a proper sense, but it has some good, interesting structure.
Another question, it seems like that when is there negative dependence? Well, you know, as in your examples, there's sort of some implicit resource that gets used up, right, when an event occurs and precludes another event, right? The ball goes in one bin and can't therefore go in another. And so,
Yeah.
so I just wondered if there's some, if one had an analysis of the underlying resource, maybe like in the semantics could address the issue that, you know, the natural functions at the level you formulated it are non-deterministic, but maybe there's an underlying resource analysis then that would fit more with a usual separation algebra. I don't know if I'm making any sense at all.
Yeah, so I mean, I think, let me see if I understand. So for sure there is a notion of, I agree with you that there is a notion of a resource, and that is what brought us to separation logic in the first place. Now, it seems that what you are wondering is, what we do is very specific about the distribution model. And so we have distribution, and we have the joint distribution, and we have this notion of these natural non-determinists that come into the picture and so on. Now, it seems that what you're wondering is, do we have a separation logic independently from the distribution model where this kind of a negative relation could be useful? Is that your question?
Right. Or if you knew that there are distributions over some resource and that accounts for the negative dependence between the distributions.
Yeah, I don't have a clear answer. I think it's an interesting question, and there is for sure a lot to do here. Yeah, I don't have an answer for that.
I was going to ask if you could explain the consequence step in the proof again. So you have two different separating conjunctions in your assertion language.
Yeah.
And I would assume there would be a proof rule or something that relates to proof, but with the proof it seems like you're just using consequence.
Yes. So yeah, I think it's this step here. So we reuse the rule I showed you before. That is the rule that sample uniformly and give independence. So it was the rule from the probabilistic separation logic paper. And then I said, okay, but we can use a consequence to say that mainly the fact that we have independence give us the fact that we have a negative association. Now you're asking where, so the rule we use is consequence, is the classical consequence of separation logic or logic. But now I think your question is why you have this implication here. So, and this implication can from the bunched logic setting. So in the bunched logic setting, we have this. So we have that if we are given something that is independent, we can derive a negative association. Okay. And this is one of the properties we have to build our model to validate. So our model validates this property, and that's why we use it.
So one last, maybe tiny question.
Sure.
One of the cool things about separation logic is that people have found lots of ways to build automatic tools for it. But I get the impression these are by hand. these proofs?
So they are by hand.
What's it going to take to?
Yeah,
Not be
so let's see. So the meta theory has been formalized, but that's another
Great, cool.
is another question.
It's hard work.
So we have wondered if trying to integrate this in Iris, for example, because one of our collaborators is an Iris expert. Iris is this higher order separation logic reasoning and most. I mean, it's a higher order general separation logic where you can define invariant and so on. Now, the problem is there is not really like, one can try to hack it a bit and try to have this notion of distribution. So maybe what we are missing is distribution. And so you would need to axiomatize a part of it and then try to play with it. Yeah, it's something we should do. So we didn't do yet, but let's maybe think about what this would imply. So I think that, I mean, maybe it would not change too much the way you're reasoning about in Iris. But Iris maybe is not exactly what you were thinking.
No, that's still proof by hand.
That's still interactive. But
Even in Iris, isn't there only one separating conjunction?
Yeah. You will need to modify. That's what you will need to modify. Adding separating conjunction and change some of the rules, add the distribution and so on. That's why we didn't do it, because it's a non-trivial, even for expert of Iris, is non-trivial. Now, maybe we didn't think too much about automation, but what I expect is that the automation of this part of reasoning, so the reasoning about negative dependence, should not be bad. I think you can still automate it. Yeah. So that's exactly for me what is nice about this work on probabilistic logic, is that you encapsulate the probabilistic reasoning in black box part, and then you can just do logical reasoning. And I think that the algorithm that worked for separation logic would work also for this, mainly because the real algorithm is the algorithm for bunch of logic. To solve this kind of, this can be automated. Right. And I expect that maybe you need to add a few axioms, but once you add a few axioms, also this can be automated.
To make sure I got it, so you would have to enrich the domain of whatever prover so you could talk about distributions.
Yes.
When ideally a bunch of things.
Oh, no, that's in the meta theory.
It's only in the meta theory.
Yeah, the distribution is only in the meta theory. What you need is something, so you need to enrich the solver for a separation.
Sure, okay, the logic language, that's what I meant. Not of the, right. The logic needs to be enriched to talk about some notion of distribution, like you'd have this notion of one hot.
Yeah, sure. But these are symbolic.
Yeah, purely symbolic.
Yeah.
And then you would use solver techniques like whatever form of inference or graphical model or whatever makes you feel